it's an auditorium camera because I only see onto the auditorium, but I only see the speaker, which is empty. But I'm not sure if that's okay. Hello. Yeah, sorry, there's sun coming in here, and I just can't block it, unfortunately. So. Okay, so first of all, yeah, thank you for the kind introduction, and I'd like to first of all start by saying I deeply apologize for not being able to come. I just said already to Andrea, I have a 1-year-old son, and my wife's most important conference is taking place today, and we could not both travel, so I'm home with my son, and she's traveling. So that's why I actually very much appreciate that I'm still given the opportunity to talk to you here online, even though I'm of course missed the in-person meeting. I also like to upfront say I'm very grateful actually to be part of this program. Actually, the AFOSR program has helped us to strengthen collaboration with my collaborator Sunil Bava, whose joint work I'll be presenting today. And also should mention, given our tension relation in Switzerland with the European Union, our funding landscape has significantly become more complex, and that's why I appreciate actually even more being part of this program. So without further ado, what I'd like to do actually in the next half hour is tell you about work that we have been looking into concerning non-reciprocity and integrated optomechanical systems, which is really trying to unite the world of MEMS technology, as Sunil Bava is working on, our collaborator, together with integrated photonics. I'd like to mention that even though this MURI review is mostly about non-reciprocity, I still would like to mention that there's some very interesting applications of this temporal modulation that we're exploring also commercially. I'd like to just mention that we started a new company called DeepLight that's commercializing some of the technology of MEMS integrated with integrated photonics for applications in FMCW LiDAR. Okay, so I'd like to start very briefly by just outlining kind of the key platform I'll be discussing, which is silicon nitride. And silicon nitride is a material that's well known in the semiconductor industry. It's been used as a protection layer, end cap layer, or edge stop. It's CMA certified, but it's only been very recently, restarting with the work from Michal Lipson, that it has been explored in integrated photonics. And one of the challenges for integrated photonics, in particular for tightly confining waveguides, are the growth of thick nitride, which has been only become possible over the last decade when investigating techniques to control the very large stress that is innate to LPCVD nitride. Now, why is silicon nitride interesting? Well, in contrast to silicon, it has a band gap of 5 eV. It's a material that has a relatively high refractive index. It's CMOS certified. It has a transparency window from mid-IR to visible. It has a high effective nonlinearity, about 100 times larger than fiber, and no two-photon absorption in the telecom band. Over the last, really 10 years, there's been a very rapid proliferation of experiments in the field using silicon nitride. And starting with work really by Michal's group in 2010, it's been shown that you can use this material for carrier frequency combs and thereby explore nonlinear photonics. And very quickly, actually, the palette of possibilities and the capabilities of the material has been extended, notably by reducing losses, which I'll briefly talk about, by adding piezoelectrics, which is the second key ingredient I will discuss today. And also in most recent work from my group, actually, we have been able to endow the platform with gain by applying erbium. And not just gain by erbium can be explored, but also parametric gain by just the nonlinearity itself. And these last two results, actually, I will not have time to discuss today, but they are actually very related to some of the work we're doing in this MURI, because erbium gain is bidirectional, whereas parametric gain is unidirectional. So, and we can directly compare the advantages and opportunities, actually, of unidirectional amplifiers. When it comes to back reflection from facets, it's a significant advantage to have devices that are unidirectional. So as I said, integrated photonics based on silicon nitride has really seen a lot of activity over the last years. Initial work was mostly motivated by the generation of carrier frequency combs and more recently Salta microcombs. But there's been more use cases for silicon nitride, in particular due to the ability to achieve low loss in the area of narrow frequency agile lasers that can particularly be used for LiDAR, low noise microwave generation, broadband parametric amplifiers, or endowing the platform with further functionality, such as bonding with lithium niobate, or as I will discuss today, adding functionality via piezoelectrics. The platform is also commercially available. In my group, we started a company about 6 years ago, Leichentech, that's commercializing silicon nitride, and which is used by both academic customers but also by industry, as shown in this paper here from Xanadu, where our silicon nitride devices from Leichentech were used in a photonic quantum processor. Now, together, one challenge in general in integrated photonics has been to achieve low optical losses. And the ability to achieve losses that are, so if one compares, for instance, the loss that one obtains in optical fiber versus losses obtained in indicator photonics, what is striking to see is that until a few years ago, there's been a discrepancy of about 5 orders of magnitude. So in fiber optics, we have 0.2 dB per kilometer loss that allows us to actually have today this talk online, whereas in integrated photonics, until about 5-6 years ago, the state-of-the-art losses, say in silicon photonics, were dB per centimeter. And there's been a lot of progress in the community into developing very low loss integrated photonic circuits, which have applications ranging from very narrow line with lasers, Kerr-Salt on frequency combs, as well as to complex and dense integrated photonic circuits. And while there's still a large discrepancy between integrated photonics and optical fibers, the latter could be reduced by about 100-fold improvement over last years by several labs around the world by exploring tightly confining waveguides in silicon nitride. And so the way we achieve very low loss in our lab is by having developed a so-called photonic damascene process, a process that allows us to achieve very low loss negative photonic circuits while avoiding most of the surface roughness. The way this process works is using a well-known process that's been explored in VLSI, so large-scale integration electronics, whereby, so the lower right picture shows here a cross-section of your Pentium processor, where where you see the copper interconnects and the silicon wafer in blue. Now this process uses a preform where you fill copper into. We use the same process, but not fill a metal, but rather dielectric. And that's why it's not called the copper damascene process, but rather the photonic damascene process. And one of the nice advantages is that one can avoid, in this case, the difficulties that encompass silicon nitride, in particular the high stress that causes crack formation. Now this problem still requires etching of a preform, and so one of the distinct advantages of using silica as a preform is the rather low glass softening temperature. And so what we can do with the preform is heat it up to 1250 degrees and slightly reflow kind of the edges and take out all the roughness of the silicon nitride waveguides. And this actually works strikingly well, this technique. With this, we can now generate integrated photonic circuits that are literally meter long with losses of less than 3 dB per meter. And here you see, for instance, a spiral waveguide with 1 meter length that can be dispersion engineered by changing the waveguide dimensions, which has a loss here below 3 dB. And so these devices themselves are exceptionally nonlinear. I will not have time probably to review it, but they are themselves actually, they can be used as unidirectional amplifiers simply by pumping them near a zero dispersion point to generate parametric gain, and thereby realizing a unidirectional traveling wave parametric amplifier. And so we've shown this actually in recent work that I probably will not be able to review, but it has a distinct advantage of giving amplification that's unidirectional, does not suffer from back reflection or from facets. Now, we've combined this platform over the last years in a continued effort together with the group of Snil Bave with MEMS technology, in particular with aluminum nitride. And the vision and idea has been to add temporal modulation to our platform. And so there's a number of techniques that we'll hear today, how to endow integrated photonics with temporal modulation. One very successful approach is evidently lithium niobate, which directly has an electro-optic effect due to the Chi2. Here we treat a material that has elemental nonlinearity Chi3, so there's no pockets effect, and so we have to endow the platform with further functionality. In this case, we've done so by adding aluminum nitride as a stress optical material for performing stress optical modulation or actuation of the silicon nitride. And so, first of all, very briefly, ALN is a material that's very well known in the microelectronic industry. In fact, it's used ubiquitously in F-bar and H-bar filters. So it's a foundry-based process. Aluminum nitride in particular has a distinct advantage of being a highly linear material. It has no hysteresis. So up to gigahertz frequencies, actually it's a purely capacitive load, and as a result also ultra low power. Now the technique, the ALN is very used for MEMS filters, and together with Tobias we have shown that we can combine the ALN actuators actually on top of the silicon nitride stack, the photonic stack, while still retaining the very large optical quality factors. And this allows, on the one hand, to actuate directly the underlying photonic layer via the stress optical effect, but also, as I'll describe later, it allows to actually launch H-bar mode, so high overtone bulk acoustic resonances, okay, in the silicon photonic stack. So this technique of fast actuation can, as mentioned, takes place in a regime of very low optical losses, and so we can still, for instance, generate solid on frequency combs, and thereby generate, for instance, a solid on frequency comb that can be actuated with very high actuation frequency. Very briefly, only on the technique. So again, we can perform this process really at the wafer scale, so really at the 100 millimeter wafer. And the catch is that both processes are foundry level. So in principle, the entire technology that we have is something that can be done completely fabless. And even though it's irrelevant for the talk I'm giving today, I would still say it's important actually for transitioning technology, and in particular, as I mentioned, for building very compact FMCW lasers, it's advantageous to work with a platform that is only foundry level. So what can we do with this? With these actuators and with this temporal modulation? We've shown in the past that we can use it to control the properties of solid and microcombs directly via the stress optical effect of the aluminum nitride actuator. So we can initiate soliton formation, control the duration of the solitons by changing the laser detuning, and also actuate and frequency chirp the solitons as required, for instance, for doing a parallel FMCW LiDAR measurement. The aluminum nitride approach or technology is actually also very interesting, in particular when combining with low loss to make hybrid integrated lasers. And here I'd just like to highlight one result that we are particularly pleased about, where we have attained via self-injection locking of our low-loss silicon nitride platform with aluminum nitride as actuator. We've attained a laser that has a phase noise which is very similar and on par with a commercial fiber laser, which are the workhorse of fiber sensing. But in contrast to fiber lasers, which are kind of static in frequency, we can actuate this laser very fast. And very fast in this case means that we can achieve, in this case, triangular chirps. So for the experts in the audience, these actually are very important to use in a technique called FMCW. It's a laser ranging technique that gives both distance and velocity information. And we can tune the laser here and actuate the optical laser frequency that is color-coded with frequencies as high as 0.8 megahertz, while having a completely flat actuation response. And that very flat actuation response is achieved by eliminating all the mechanical modes actually of the photonic stack, except the H-bar modes, which limit the actuation frequency to about 17 megahertz. So this is going to be our underlying kind of test bed for also looking at non-reciprocity. But I want to highlight that beyond non-reciprocity, there's very interesting application of the technology that also are interesting in the commercial range of FMCW LiDAR. So what's the physics that we use for stress optical actuation? Again, this is very simple. It's our piezoelectric strain coefficient tensor that we're exploiting. In general, when you have a piezoelectric, there's two contributions. One contribution is the photoelastic effect, so change of the refractive index with pressure, and there's also a moving boundary effect. Now the moving boundary effect in our case is negligible because we have no free boundaries. Our resonators are fully kind of embedded in a dielectric cladding, and as such the only effect that gives us here an enhancement is the photoelastic effect. Even though we can enhance the coupling by undercutting the structures and creating a free oxide layer, and then we also have a contribution from the moving boundary. So just very simple. If we activate the devices, we can record kind of the coefficient here of tuning, In aluminum nitride, we typically have 30 megahertz per volt tuning, which is about a factor of 10 lower than what can be achieved with, say, lithium iodide via the Pockels effect, which is still decent and allows us to achieve, as mentioned, a decently large frequency excursion sufficient for applications such as FMCW and also for non-reciprocity, as I'll describe. Now, as mentioned, these piezoelectric actuators, they launch sound wave. And so for some applications, you wish to actually avoid the excitation of mechanical modes. So what's shown in gray here actually is the bare chip. So you can see that the actuation response of the optical frequency is far from being flat. In fact, there are many mechanical modes. And these mechanical modes all come from the chip itself, in our case, a 5 by 5 millimeter photonic chip. And so by apodizing these chips, by making the chip in a fashion where two faces of the chip never face each other, we can remove most of the mechanical modes and thereby achieve, as shown in blue here, a very flat actuation response up to 10 megahertz, which is within here, well within 1 dB or even less, up to 10 megahertz. So it shows again this very flat actuation bandwidth that we have with ALN. So having endowed the photonic platform with aluminum nitride as an actuator, as I described, we have on the one hand a very promising platform for instance, looking at laser-based ranging by using self-injection locking, but we also have a platform to look at non-reciprocity. And that's precisely the effort that we have engaged with Sunil Bhava over the last years. And for this, we have used kind of one more ingredient, which is not just a stress optical actuation, but in fact we are exploiting resonant phonons actually off the photonic stack. And in this case, these are so-called H-bar modes. So these H-bar modes are confined by the two interfaces of the silicon wafer. The actual stack is a bit more complicated because we have aluminum nitride on molybdenum, on SiO2, on silicon. So all these three have different acoustic velocities. And as such, we actually form nested cavities. So if we do a S12 measurement where we launch via the aluminum nitride electrodes microwaves and look at the reflection properties actually from the ALN actuator, what we see is first of all, the H-bar modes, which are spaced here by 17 megahertz, so they're very densely ones. And we have a supermodulation that can be seen, which actually comes from the cavity that's formed by the SiO2. And so the 17 megahertz we see is actually commensurate with the 5 micron thick kind of silicon stack that we have. So we'd like to actually explore and exploit now the coupling of one of these H-bar modes at gigahertz to these high Q optical modes. And we can also, as mentioned, actually undercut the device to increase the optomechanical interaction and in particular decrease the mode volume. And so the smallest mode volume of an H-bar that we can make is simply to use a dielectric cladding actually of the silicon nitride, whereby the G0 here reaches value as high as 200 hertz. So this G0 here is the vacuum coupling rate, so the amount of frequency shift that the vacuum fluctuation of the H-bar mode that's confined now in this dielectric stack is causing actually onto the silicon nitride. And so these are not particularly large numbers, but not particularly small ones neither, if one takes into account that we can pump actually these optical resonators with very high photon number. So silicon nitride, due to the large quality factors I've described, can sustain photon numbers that are well in excess of 10 to the 6 and 10 to the 7, which leads to a large enhancement of the effective coupling between the mechanical modes in the dielectric stack here and the optical mode. Now, so in this program, what are the devices we have explored? In addition to the FMCW or frequency agile laser I've described, has been to create an isolator. And towards this end, what we have looked at is a slightly more complicated device, whereby we have our silicon nitride ring actuator, a micro ring cavity, and we endow it now with 3 different actuators. So these are 3 different ALN actuators, spaced in close proximity. And one very interesting property that we explore in this work is the fact that ALN H-bars, or the high overtone bulk acoustic resonances of adjacent actuators is actually very well decoupled. So the amount of isolation one has from one actuator to the next is about minus 60 dB. And so there's hardly any crosstalk between them. And this allows now to realize ideas in literature that have been proposed by many actually in the audience, in particular by Shan Hui, but of course also Andrea, of looking at not just temporal modulation, but in fact momentum biasing. And so again, this is well known to to this audience, so I will not spend much time on it. So we achieve momentum biasing here by making these three actuators and driving them out of phase with 110 degrees. And as described, we have very high Q optical resonances. So coupling now a gigahertz H-bar mode to the optical cavity will become very inefficient unless two optical modes are split exactly by the mechanical frequency. And the way we have realized this in this actuator is exploring or exploiting the intrinsic and innate TE-TM coupling. So if the TE and TM mode are degenerate in frequency, if you make the waveguides a square, in fact, you will induce coupling between the two of them and generate the splitting. And as described, we can increase the coupling now, the scattering induced by the optomechanical system by the square root of the photon number in the cavity. So while this G0 is only 200 hertz, if you make the photon number large in the cavity, we can achieve very sizable kind of megahertz coupling rates between actually the optical, these two optical modes and the mechanical H-bar. So we have used this scheme to generate non-reciprocity, and another important condition actually is momentum matching. So the two modes, the T and TM here, they differ by an angular mode number actually of 1, so that actually the rotating momentum that we impart by these three actuators directly compensates a momentum mismatch. And this technique works. We've demonstrated in this paper that was published actually last year, and kind of shown that you can this way generate in the forward and backward direction. You can generate non-reciprocity. It extends over up to several gigahertz of bandwidth we have demonstrated. And what you see here is kind of the detuning, normalized transmission in the forward and backward direction. What you can also see is that we can reconfigure the non-reciprocity itself. So by changing actually the phases here, we can go from a completely kind of transmittive to a completely absorptive state actually in the forward and backward direction. So this is kind of a nice proof of concept experiment that we've demonstrated, showing that the ALN MEMS technology can be used to implement momentum biasing and also be used to generate non-reciprocity. Now, in the last kind of 10 minutes, I'd like to switch gear a bit and tell what other experiments we are interested in, which build on this work of non-reciprocity, of combining MEMS with indicator photonics. And so one field that we have been closely following and we are very interested in is to demonstrate and explore novel ways to interrogate superconducting qubits. And so one of the challenges right now in superconducting circuits is how to interface hundreds, potentially even thousands of superconducting qubits that are sitting at millikelvin temperatures inside a dilution fridge. And similar to optical fibers that already pervade data center interconnects and are replacing electrical cables, one can also ask the question, is there an opportunity for indicator photonics to replace the microwave cabling that one is typically using to connect the microwave world of your controlled drive electronics with the superconducting circuits at millikelvin temperature? And so here our vision is, can we use the ALN MEMS with indicator photonics to read out and also to convert microwaves to the optical domain? And so, again, as a bit of motivation, why indicator photonics could be very interesting, let me show this example here of IBM, where there's literally hundreds of coaxial cables, which each actually impart about a milliwatt of thermal heat load or thermal conduction from the environment, whereas a similar optical fiber would have a thermal conduction of only 10 microwatt. So this makes optical fiber very distinct. They're excellent optical conductors. They're 0.2 dB per kilometer loss, while at the same time they're very, very poor thermal conductors, which is precisely what makes them interesting and attractive to study in the context of superconducting circuits that are very sensitive to the outside world in terms of temperature fluctuations. And so the current state-of-the-art readout is based on HAMD amplifiers together with microwave cables, and we and others are interested to replace these devices actually with indicator photonics for doing the conversion from the microwave to the optical domain. And so these microwave-to-optical transducers have applications also beyond quantum information processing with superconducting circuits. They can be used for radio astronomy, microwave photonics, or also kind of other applications in the realms of quantum sensing. And so there's been a lot of interest and a lot of developments also from people in the audience, such as Amir Safeni, on realizing such transducers in either a purely optomechanical platform that's coupled to electromechanics, and a purely Chi2 based platform. You'll hear later from Amir, I think, about this, and also a platform that are hybrid, which is combining piezoelectricity and optomechanics. And so we have been interested in the last approach, so exploring our aluminum nitride platform and integrated photonics for the purpose now of microwave to optical conversion. And so what we have engaged in is to use the same H-bar mode I've described before, so a very high frequency mode here at several gigahertz, coupled to a silicon nitride optical waveguide. And what we can do now is inject microwaves, and drive the actuator via the top and bottom electrode and convert incoming microwaves to optics. But similarly, we can also drive the system with optics and convert it back to microwave. So it can be a completely bidirectional system. And what makes our approach interesting and distinct is that we have very efficient coupling from microwaves into the phonon. Effectively, we can fully impedance match the drive line and fully extinct the incoming microwave field and convert it to a mechanical H-bar mode. So we're very efficient on the input to output coupling to the phonon, and by achieving large optomechanical coupling, we can now convert and try to convert that phonon within its lifetime to an optical photon and to create a bidirectional link. And so effectively, what the system is, it's an optomechanical system. One has as such the full optomechanical toolbox. One couples the photon number A dagger A to the mechanical oscillator coordinate, which is now the H-bar. And as such, one can use the system to generate either a direct conversion, so beam splitter Hamiltonian, or by annihilate, in this case, phonon. You can also use it for QND measurement or entanglement, where you generate pairs of photons and phonons in the system. So it has the full toolbox of optomechanics available in the system, except for one kind of aspect that needs to be taken into account, which is the fact that to couple efficiently a gigahertz mechanical mode to optics, one needs two optical resonances. And this can be simply understood by noting that an optical laser field actually would be red detuned by the mechanical frequency would actually be very far detuned and have very little and cause very little intercavity photon number. So our system again is one where we try to split the two optical resonances, and whereas for the the isolator work we used a TTM mode. What we've done here, we have taken actually two optical modes from two distinct resonators, made them frequency generate to cause a splitting. And so I'll be a bit faster. So this is our device. So we have two rings, in this case, two ALN actuators. And what we can, these two rings actually are brought in close proximity to produce a splitting that is in the range of gigahertz, and that matches the frequency of the underlying H-bar mode. And with this device, we can produce splittings on the range that are tunable, on the range of a few gigahertz. But importantly, we can retain a line width that is below, in this case, 100 megahertz. So we have kind of very high Q optical resonators that allowed to achieve large circulating powers. Now with this system, now we can look at frequency conversion, and we've done that. In two ways, either by inserting or modulating, sending RF actually into our ALN actuator in our H-bar mode and convert it into optics, or conversely, by applying a modulation to the optical input and converting that back to a microwave. So it's a fully bidirectional interface. And so very briefly, because I'm running out of time, we have shown actually that up and down conversion they should behave exactly the same. There's a slight difference, which I won't have to go into time to explain. The conversion efficiency here is about minus 55 dB, so still significantly lower than what we would like. But in this first series of experiments, we have hybridized the H-bar with actually the entire bout modes, and we have taken a large penalty in our G0. We can now look also how well this approach compares to other approaches in the field. And as I said, it's a very active field. We are still very happy that our first device actually produced on-chip efficiency of about 10^-3 with tens of megahertz of bandwidth, which compares quite favorably, in fact, to other platforms that have recently been demonstrated. What is interesting about the approach is that we can still increase the coupling quite significantly by at least a factor of 100 by exploring even larger G0s, which will be able to be attained in the several kilohertz regime, and by exploring even larger optical quality factors. In the last slide, I want to show a very recent experiment that we've carried out. that shows that we can not only use the device to convert microwave field to optical field, but we can also use the device to generate microwaves. So as a microwave generator, synthesizer. And so in this experiment, what we've done actually, we've inserted 2 optical pumps into our hybrid transducer and generated and looked at the output of our transducer. So what happens here is that there's a polymotive effect that generates an H-bar mode. This H-bar mode is converted to electricity via the piezoelectric effect. And this can be just picked up with an electrical spectrum analyzer. So this is microwave emission here, at this case about 3 gigahertz, that we purely optically generate. And when we modulate these microwaves, these optical fields, we can also actually generate microwave pulses. So we have a completely kind of optically synthesized microwave that we can use, for instance, to drive superconducting qubits that is now generated in situ inside, say, an optical dilution refrigerator. So in summary, you're running out of time. We've looked, as said, with Nobave at applying ALN to indicator photonics. We have used that platform to generate a transducer, also look at FMCW laser ranging. And what I won't have time on to discuss is we've also engaged in looking at both the ability to create bidirectional amplification and unidirectional amplification in photonic integrated circuits. And have seen that unidirectional amplification overcomes one of the key issues of indicator photonics, which is reflections on the facets, and have work ongoing to explore this even further. With this, I'd like to thank the team, and in particular also our collaborators, Sunil Bave, Hao Tian, and Elena. And I'd like to thank you again for your attention. And again, I deeply apologize. I would have very much liked to attend this meeting. But my duty as a father are the moment here required at home. Thank you so much.